Hello there, this is Mr. Stark with a video lesson on parametric curves, part of a TrigApps unit. Now what's in front of you are parametric equations. Usually they come in pairs, and one defines the x value and one defines the y value. Now if we're in 3 dimensions, there could be a z value. Now don't be confused by this notation. F of t simply means it's a function based on t. So x, the value for x, is based on some function based on time. And the value for y is based on some function g based on time as well. So time is the parameter that we're focusing on. And so when we say parametric curves, we mean the actual graphical curve that we see. And we also include line segments or lines in that category. Now, because that's the only shape, I guess you'd call it, that's not like the others, we still just call them parametric curves. And what's in front of you is the parametric set of equations. Okay, let's move on. Let's take a look at how to just start with 2 equations and begin to graph them. So here's an example that gives you 2 equations. X equals some function based on time, and y equals some function based on time. And then we give this window that the graph is actually operating under. That really highlights the powerful nature of parametric equations, the ability to sketch a curve only on a specific window that we care about. And now this could actually help model situations. You have some data that you want to model, and many times in mathematics we need to say, all right, we're going to use this equation, but we're only going to use it on this window. So this allows us to actually sketch exactly what we want to. So now because it says on the window from -2 to 2 inclusive, those are the values that we're actually going to plug in to the functions. So I chose each integer value. It would be crazy if I chose half values like 1.5 or even other crazy values like 0.2. Let's just start with these values and see what it gives us. Now what we'll do here is we'll take each t value, plug it into each of these functions, x and y, and then we will have points that we can sketch on the coordinate plane. So it just changes our table. Instead of having just x and y, we'll have t, x, and y. And really this x and y is just to help us sketch the point. So what we'll do is we plug in -2 into t squared minus 2. So -2 squared is 4 minus 2 equals 2. We'll do the same thing with -1. -1 squared is 1 minus 2 is -1. And we'll go straight down the line. 0 minus 2 is -2. 1 squared minus 2 is -1 as well. And notice I just start doing some of the work in my head. So now I have 5 x values, 2, -1, -2, -1, and 2. Okay, now let's do some y values. We'll take the same t values, plug them into the y equation, and we have some basic values there. So 3 times -2 is -6. I'll do the rest in my head, which becomes -3, 0, 1, and 3. Just kidding. That would be 3 and 6. And I noticed that because I knew there was some sort of symmetry going on inside the graph. Okay, now I'll just take those points and I'll create my, those individual points, and I'll create the ordered pair. So 2, -6, -1, -3, and so on. So I have 5 ordered pairs, 5 points that I'll actually plot on the graph. And before I go any further, I'm going to notate that this first point is where the curve starts. And that's only because we're working with parametric equations and we're starting at -2 from left to right up until 2, and then we're going to end at 2, 6. Okay, so that shows you the progression of the data points. And this will come in handy, especially when we look at some examples later, dealing with someone hitting a baseball, maybe in an actual game where they hit the ball and it starts when they hit it and it ends when it drops. Okay, so now I have a coordinate plane, and usually I would label each point as 1, but my graph doesn't quite go up to 6 up here at the top, so it's going to be a little skewed. So I'm looking back at the previous page here, and I want to plot 2, -6. 2, -6 is what I'm going to plot. 1, 2, 3, 4, 5, 6. And I have a point over there. So I'm going to label that as the starting point. -1, -3. 1, 2, 3. -2, 0. -2, 0. And now watch what happens. We have 3 points down below, and now we hit -1, 3, which is directly above that -1, -3. So you could expect, even just not looking at the table of values, we're going to get 2, 6. 2, 3, 4, 5, 6. Okay, and I look at it, and that's 2, 6. So that is where the curve ends. And now what I'll do is I'll sketch the curve exactly how it happens. It starts here. It's going to curve around like a boomerang and come back and end at 2, 6. And usually what we'll do with parametric equations and curves is we'll sketch these arrows so it communicates the actual direction that things are happening. This is where I'll just take a moment to say, well, if we're programming something like some sort of particle or some movement inside of a program, a game, or some software that someone's running, then it is exactly what we want to do. We want to make a particle move based on the movement that a human makes. So that's the very first thing that we'll do with parametric equations, is just plot the points on a coordinate system. What I'd like to do next is show you 2 examples. One is a fairly basic example, and the other one is a common example that we'll see with trig. So both of these examples deal with eliminating the parameter. And basically what that means is we have 2 parametric equations, and we want to write them in terms of x and y, a Cartesian equation based on René Descartes' original graph. Alright, so what the first thing that we'll do is we'll solve for t. Now it doesn't really matter which equation I solve for t in, but usually it's the x equation that we'll want to do that in. Alright, so I'm going to do that, and I'm going to say x minus 1, I'm going to subtract 1 on both sides, is equal to t. And then I'll take that defined t, I'll take that x minus 1 and plug it in as t into the other equation. So now we have y equals 2 times t minus 1. Of course we don't. That's 2 times x minus 1 because we're eliminating the parameter. Okay, so t is what I replaced in y equals 2t, so then I get y equals 2x minus 2. 2x minus 2. And now that goes on forever. That's an equation that, because the t is defined from -infinity to infinity, that is a line that starts, well, it doesn't really have a start and an end. Okay, so that's our Cartesian equation, Cartesian, and it doesn't really have a start, doesn't really have an end. Okay, so if we wanted to, we could limit it, we could place restrictions on it, but we don't really care about that right now. So, but some of the equations that you'll come across in eliminating the parameter is you'll have some sort of parametric equations that are defined on a certain window, and so that means it's only going to show up in that particular window. But we don't necessarily know the x and the y values. So we would use the t values in that window to identify what the possible x values could be. Basically like finding domain and range. So here's the last thing in this video, and it's an example about a set of trig parametric equations. And notice how we have x equals 3 cosine t and x equals 3 sine t. Now remember, because you've studied trig before, that sine and cosine are circular functions. So the way that they interact with t and x would be in a circular sort of motion. So that either means they're sketching some sort of triangles or creating a set of points that will be curvy. So in order to eliminate the parameter in this particular case, what we need to do is be very intentional about our steps. The first step is to isolate cosine and sine. That means I need to divide by 3 on both, or for both equations on both sides. So x over 3 equals cosine t, and y over 3 equals sine t. Now notice over here, by the way, this from 0 to 2 pi is the window for t. And that's because it's going to complete a full circle of, basically a full circle. Okay, now the next thing is we're going to square both sides. And what that looks like is this. I'll just do some of that stuff in my head here. X squared over 9 equals cosine squared t. And y squared over 9 equals sine squared t. Remember that notation, sine squared t means the whole quantity, sine t squared, just a shorthand. If you didn't watch this video and you weren't taught specifically how to do this, it would have been pretty difficult to come up with this. But the next thing is the key part of this whole thing. It's to add the equations together. And that looks like this. I'm going to add the green parts together, and I'll add the red parts together here. Alright, so hopefully you can follow along here. So that becomes x squared over 9 plus y squared over 9. And if we add the left parts of the equation, they must be equal to the sum of the right parts of the equation, the right sides. Okay, so notice that those green pieces are on the left side of the equation, the red pieces are on the right. And furthermore, notice, we're going to kind of go to the left here so I could have enough space. And furthermore, we have x squared over 9 plus y squared over 9 equals, oh my goodness, cosine squared plus sine squared is 1. Almost done here, wrapping this last piece up. Thanks for sticking with me. So, when you look at this equation, you may not know what it is, but I think if I write it in this last form, you would know what it is. X squared plus y squared equals 9. And that, my friends, looks like the Pythagorean theorem, and it basically is. It represents every single right triangle that has a hypotenuse of 3. In other words, it's a circle, a locus of points, a circle of radius 3. Hey, that's pretty neat. If we have equations that look like this, that is how we create a circle in parametric mode. And then we could make it sketch one circle, or if we go up to 4 pi, it'd sketch 2 circles, or 6 pi, 3 circles, and so on and so forth. Or we could sketch a half circle if we wanted to, which we would go from 0 to pi. Alright, now this equation, x squared plus y squared equals 9, is a Cartesian equation because it only has x's and y's. Alrighty then, well that's all I wanted to share in this particular video, so thank you so much for watching.